Hi everyone, I'm Dina, and this presentation is on heart rate. First, I'll go over some of the basic principles of heart rate to help you understand the readings and the remainder of this lesson. Heart rate is the speed of the heartbeat per unit of time. It is usually measured in beats per minute, but can also be measured in hertz. Hertz is the SI unit for frequency, measured in cycles per second. Therefore, if you know beats per minute and you want to convert it to hertz, simply take the amount of the beats per minute and divide by 60. Likewise, if you have the hertz measurement, you can multiply by 60 to get beats per minute. Heart rate varies according to physiological needs. Every physiological process requires the production and consumption of ATP, which requires a steady supply of oxygen. In warm-blooded animals, heart rate is inherently linked to metabolic rate, as the lungs deliver oxygen to the blood and the heart circulates the oxygen throughout the body. The relationship between heart rate and metabolic rate can best be explained using surface area to volume ratios. Smaller animals have a higher surface area to volume ratio than larger animals. The higher this ratio is, the faster the metabolism will be, and the more frequently the animal will need to breathe in oxygen, requiring a faster heart rate. This is why the canary has a much faster heart rate than the horse. Heart rate also varies with activity. The animals shown in the chart are at rest. Notice that the crow has a resting heart rate of 300 beats per minute, while the hen has a resting heart rate of 312 beats per minute. If the crow were in flight, its heart rate would easily surpass the hen's resting heart rate. If we know the relationship between heart rate and metabolic rate for an animal, then we should be able to quantify the energetic costs of different activities by simply measuring heart rate. Using heart rate to estimate the metabolic rate of free-ranging animals, or field metabolic rate, is known as the heart rate method. This may be presented as oxygen consumed per day. The Fick's principle is the basis for this method. It states that the volume of oxygen consumed is equal to cardiac output, which we measure by heart rate, times the amount of oxygen used by the muscles. Our first study is by Froget and Associates 2004, Heart Rate and Energetics of Free-Ranging King Penguins. King penguins are the second largest penguins after the emperor penguin. They live in densely populated colonies, mostly on subantarctic islands. The main purpose of this study was to measure heart rate to determine energetic costs of behaviors of king penguins while incubating ashore and foraging at sea. A secondary purpose was to estimate their rate of oxygen consumption while diving using heart rate and then use that value to get the calculated aerobic dive limit for king penguins. The study was conducted during the king penguin breeding period, which is the longest of all penguins, and it usually lasts about 14 to 16 months. That's how the study was done during one breeding period, but was conducted during 2 consecutive austral summers. Austral summers run from November to March. They're the summers of the southern hemisphere. Really, Antarctica only has 2 seasons, summer and winter. The summer months, of course, are the warmest and the sunniest, and so it's easier to observe the wildlife. Observation was an important aspect for this study, as diving bouts of king penguins were visually determined. 27 king penguins were captured for this study. They were implanted with custom data loggers that could measure heart rate and hydrostatic pressure to record diving depth. The data loggers had a memory of 4 megabytes and were programmed to record this information every 2 seconds. The loggers were 61 by 24 by 6 millimeters and weighed 27 grams. To put this into perspective, a 4 gigabyte USB jump drive is about 55 by 17 by 9 millimeters and weighs 12 grams. so they are pretty close to the same size, but the data loggers are somewhat heavier. They were basically electrocardiograms that were able to also measure depth. A circular fence of wire mesh was used to enclose the king penguins for capture. This protected the bird's territory as well as the bird from predators, especially those that occur more frequently during the breeding season, like skua and giant petrels. Once a bird was captured, it was anesthetized so that it could be weighed and the data logger could be surgically implanted. The anesthetic that was used was halothane in a 1-to-1 mixture of oxygen and nitrous oxide. Halothane can be used on people, but it is used most often in veterinary surgeries. 2 incisions were made, one in the abdominal cavity to place the data logger and one of the 2 electrodes attached to it. This first electrode was actually placed near the apex of the heart. The second incision was done 3 centimeters above the brood patch, where the second electrode was placed. The brood patch is that featherless area of skin usually on the underside of nesting birds. On penguins, the brood patch is located on the lower breast area. The brood patch is much warmer than the feathers, so the king penguins place their eggs on top of their feet and against the brood patch for warmth. Once the data loggers and electrodes were in place, their position was checked with an endoscope. All of the loggers were checked to make sure that they were accurately recording the heart rate before the penguins were sutured up. After surgery, the eggs were swapped with plaster eggs, while the real eggs were placed in an incubator. This was done to protect the egg after the surgery, just in case anything happened to the birds. The fence around the bird was removed when the anesthetic wore off, which took about 5 hours, and then the egg was replaced either the following day or the next day. The birds were recaptured the same way that they were initially captured, with the wire mesh fence, and the position of the data loggers and the electrodes were checked to make sure that they were still in the correct positions. For the 27 birds that were initially captured, only 25 were recaptured. The pressure sensor part of the data logger failed in 4 of the penguins, and the electrocardiogram electrodes had moved in 6 other penguins, meaning that the heart rate readings were not accurate for these birds. For another 5 penguins, the data loggers failed altogether, which may have been due to waterproofing issues. The data loggers were custom built and coated in wax, then coated in a high-grade silicone, but usually data loggers are encased in ceramic. The issues with the data loggers left the researchers with only 10 birds that could be used for this study. Still, there were more than 10,300 dives that could be analyzed. This amount was narrowed down to only include dives that were longer than 4 seconds and deeper than 6 meters. The first 48 hours were also tossed out to avoid using atypical data that could have resulted from the surgeries. Now that we've gone over some of the background and methodology, I want to get down to the purpose of the study. You'll notice in the reading that the study sort of skips around and goes back and forth between the 2 purposes, but I've structured it here so that I can review them in order along with their significance. The primary purpose was to measure heart rate to determine energetic costs of behaviors while incubating ashore and foraging at sea. The doubly labeled water method is often used to measure field metabolic rate, but the heart rate method was chosen for this study because activity-specific metabolic rates could also be determined without the use of a detailed time activity budget. In this case, heart rate monitoring had the added advantage of being able to record data for several months at a time. Fahlman and Associates 2004 presented 2 formulas that allowed rate of energy expenditure via rate of oxygen consumption to be measured using heart rate. One of the formulas was for birds at shore and the other was for birds at sea. Froge and Associates used these formulas to get the rate of oxygen consumption, which was converted to watts per kilogram to give the estimated field metabolic rate. For penguins, 1 milliliter of oxygen is equal to 19.8 watts if resting ashore or 18.9 watts if resting at sea. Field metabolic rate was calculated during different phases of incubating ashore and while foraging at sea, including during diving bouts, in between bouts, and an hour after a diving bout had passed. Mori and Associates 2001 defined a diving bout as a sequence of complex behaviors in which the duration, depth, and interval between dives may all be adapted for optimal foraging. For the study that we are looking at, diving bouts started after 3 dives below 10 meters with a surface duration of less than 10 minutes, and the bouts ended when surface duration was more than 10 minutes. I had mentioned it before, but the bouts were visually determined. They didn't have any sort of system to where the data loggers automatically transmitted information to some computer program to figure this stuff out. They had to wait until the study was over to collect what had been recorded on the loggers. So Froge and Associates put in a lot of observation time here to record when these bouts started and ended. Individual dives fell within 2 distinct categories: deep and long dives and shallow and short dives. The deep and long dives were more than 40 meters deep and more than 3 minutes long, whereas the short dives were less than 40 meters deep and less than 3 minutes long. Deep dives only occurred during the day, and at night the dives were shallow and short. This might be due to vertical migration of the prey fish. Overall, heart rate declined when active foraging began, remained steady during the day when deep dives occurred, and increased at night when foraging decreased. After submergence, there was a rapid decrease in heart rate for 6 seconds for all dives. Decreased heart rate helps to conserve oxygen stores because blood is moving slower throughout the body. For long dives, heart rate increased during the next 6 seconds and then began to decrease again until it became steady and similar to heart rate while ashore. For shorter dives, heart rate stayed at the lower level that was reached during the first 6 seconds, which was also similar to the heart rate while resting ashore. The increase associated with the deep dives may be due to a greater effort to overcome increased buoyancy from breathing in more oxygen to dive deeper. As the penguins dive deeper, though, the buoyant force decreases because all the little air spaces between the feathers become compressed. If you look at the table, you can see heart rate, estimated oxygen consumption, and estimated field metabolic rate for the penguins during different activities. The formulas used to get estimated rate of oxygen consumption from heart rate are also listed below the table. Looking at the data, you can see that the first hour after a diving bout has the highest heart rate and thus the highest field metabolic rate. This could be due to rewarming the body after diving. The estimated field metabolic rate from this study for penguins at sea was compared to the field metabolic rate of a doubly labeled water study on penguins at sea, and the values calculated using the heart rate method were 42% lower than the doubly labeled water study, leading Froge and Associates to suggest that doubly labeled water studies for birds and mammals at sea overestimate metabolic rates. Alright, so heart rate was used to determine estimated rate of oxygen consumption to determine estimated field metabolic rate, but how is this useful? Well, Froge and Associates explain that seabirds can be used to indicate variations in ocean resources and climate change, but to build accurate models, you need to know the bird's energy requirements. This data can be used for that purpose, as well as understanding penguin diving behavior. Now I'm going to review the secondary purpose of this study, which was to estimate the rate of oxygen consumption while diving using heart rate, and then use that value to get the calculated aerobic dive limit for king penguins. Before the study was conducted, the calculated aerobic dive limit for king penguins was believed to be around 2 minutes, which put about 45% of dives above that limit, suggesting to Frogier and Associates that this calculation must be inaccurate. They wanted to look further into this issue and try to figure out what was going on. During dives, stored oxygen is used to break down glucose to use for energy. But at a certain point, there's not enough oxygen to do this. Instead, the body produces lactate, which can be used for energy without using oxygen. This is the diving lactate threshold, also known as the aerobic dive limit. The aerobic dive limit is very difficult to measure, so instead, a calculated aerobic dive limit is often used. The calculated aerobic dive limit assumes the complete use of oxygen. It is the amount of oxygen stored divided by the rate of oxygen consumption while diving. Frogier and Associates wanted to estimate the rate of oxygen consumption and determine the calculated aerobic dive limit. To do this, heart rate values were used. Estimated oxygen stores for king penguins fall between 45 milliliters per kilogram and 58 milliliters per kilogram. These values were divided by estimated rate of oxygen consumption to get the calculated aerobic dive limit of 3.4 minutes. About 35% of the dives measured surpassed this. The rate of oxygen consumption for diving, though, remains unknown. The rates used here were for the entire dive cycles, dives, and post-dive intervals. Frogier and Associates believe that oxygen stores are greater than estimated and/or rate of oxygen consumption during diving is much lower than while resting. If the rate of oxygen consumption for diving is lower than while at rest, it could be the result of hypometabolism caused by hypothermia. Frogier and Associates explain that the significance of hypothermia has been the subject of debate, but a study on Gentoo penguins by Bevan and Associates has shown that only a 2.4 degrees Celsius reduction of body temperature would reduce the rate of oxygen consumption, so that all dives of Gentoo penguins would fit into their calculated aerobic dive limit, when 20% were shown to have exceeded it. Previously, the diving lactate threshold was estimated at 2 minutes, but Frogier and Associates determined that the calculated aerobic dive limit for king penguins is really 3.4 minutes. It was also hypothesized that during surface time in between dives, the excess lactate is used up, but Frogier found that 80% of times recorded between dives were 2.5 minutes or shorter, which is not enough time to metabolize the built-up lactate produced after the calculated aerobic dive limit has been reached. Additionally, this work may also support the idea that regional hypothermia will lower body temperature and thus rate of oxygen consumption, meaning that dives would fall within the increased calculated aerobic dive limit.